All right. So this is the chapter 9 homework. It's on momentum, conservation momentum, collisions, things like that. So there really wasn't much calculus in this homework. I did go over a sample calculus version of momentum problem with students on Friday, October 19th in class, or actually during E&I. So I really appreciate all those who came in. Um, Problem 3 here was asking about if this was your graph, force and time, what would be the impulse? Tricky thing here sometimes is it says ms, that's milliseconds. It's a little bit annoying. So that's typical collision times though, so that's to be expected. In this particular case then, we get 1,000 newtons times 0.002 seconds, and 1/2, so that's the area of this triangle, 0.006 minus 0.002 seconds, so we get a total of 4 newton seconds of impulse. With problem 13, it's asking to find this time interval. It tells you a glider is 600 grams. You can read from the graph the initial and final speed. I don't know why I didn't end parentheses there. And recognizing that the final impulse is equal to the initial impulse plus, or pardon me, the final momentum is equal to the initial momentum plus the impulse. So that's my initial momentum, that's my final momentum. My impulse is going to be 3.6 either kilogram meters per second or 3.6 newton seconds, which is more appropriate to this graph. You're given that the peak force of the graph is 36. So since this is a triangle, you can recognize that the area of the triangle is 1/2 this base, which is the delta t we're trying to find, times the height. So we now have our impulse equals 1/2 height times this base, which is the time interval, and that gets me 0.2 seconds. Problem 14 I like because it's showing one of those cases where the momentum is conserved, but the mass will change. If the mass is changing, then the velocities or speed is actually also going to have to change. So in this particular case, we have a 10,000 kilogram rail car moving at 2 meters per second. 4,000 kilograms of gravel is dropped in. I'm assuming from above, so there's no horizontal momentum because of that gravel. So because the mass increases from 10 to 14,000 kilograms, the velocity is going to decrease proportionally or inversely proportional to that. So that goes from 2 to 1.43 meters per second. Problem 26. In this case, the big idea is that the graph area is equal to the impulse. So I don't know why I started in black and then went to purple. 60-gram tennis ball hits a wall at 32 meters per second, rebounds at the same speed, so that would be an elastic collision. Again, sneaky, this is milliseconds. So looking at this, if I know my final speed is 32 and it's the opposite direction of the initial speed, that's a change in velocity of 64 meters per second multiplied by the mass in kilograms gets me an impulse of 3.84 newton seconds. So in that particular case then, that's going to equal the area of this graph. It's a trapezoid. I don't remember how to do the area of a trapezoid, but basically I'm doing it with triangles and rectangles. So that equals the area of the rectangular part, which is F max times a 0.002 second interval, plus 1/2 of F max times this time interval, and 1/2 of F max times that time interval. So essentially that means that the impulse is equal to 0.004 F max. We had found the impulse before, and so that means the maximum force is 960 newtons. P32 bookered this up, so I just wanted to show clearly that this is change in momentum with respect to time is equal to force. That's a sneaky concept that it might come back on an AP exam. Easy to forget that. So if the momentum was 6t squared kilogram meters per second, that implies that the force is going to be 12t. For 36, this is pretty cool. There's 3 different carts here. They're all initially at rest. There's a spring which causes them to explode. A 200-gram cart, 300-gram cart, 400-gram cart. This represents the motion or the position of the 200-gram cart. This represents the motion or actually position of the 300-gram cart, and you're asked to find the direction and speed of the 400-gram cart. So from this graph, you can get the speed and direction. So it's positive 0.53 meters per second. Here it's negative 0.41 meters per second. So the overall momentum before and after would be equal, since that explosion caused by the spring causes forces to be equal and opposite. So if my initial momentum is 0, the total momentum afterwards have to be 0. I don't know why I did 2, 4, and then 300, and then 2, 3, and then 400. But basically, we have a little extra momentum to the left because the momentum of the 300-gram cart is greater in magnitude than of the 200-gram cart. So that means that this 400-gram cart will be moving a bit to the east or to the right. It turns out, and I rounded a little too much here, it's going to the right at 0.042 meters per second or 4.2 centimeters per second. That number is positive, so again, that's to the right. P38, pretty neat. I answered A and B kind of together. So I did a picture, said it was a 50-meter radius where two people were running into each other on, I think it was ice skates or something like that. One was heading north, one was heading west. Called the north one number 1, the west one number 2. They hit at the middle, so that means no matter what direction they're going, it's going to take them 25 meters to get to the outside. That's the radius. So the key thing with this type of problem is keep everything in terms of momentum until the very end, because momentum is always conserved. It may not appear like the speed or the mass is conserved or is constant, but momentum always is, and so I can convert that back at the end if I want to get a speed or mass. So momentum of the first one was 187.5 gram meters per second north. The second one was 210 kilogram meters per second to the west. I get a resultant for that, which is around 282 kilogram meters per second. Since they're sticking together, I divide it by the total mass. It's about 2.09 meters per second. Using inverse tangent of this triangle, I can get that they're going to head at 42 degrees north of east. So if I know the speed is 2.09 meters per second, I know the distance to the edge of the circle is 25 meters. It's going to take 12 seconds for the people to get there. Please notice in a lot of these cases, this one not so much, although it was a little tricky with the diameter and the radius, but a lot of these are using grams. Up here I think we use milliseconds, things like that. Non-standard units are pretty typical in terms of momentum problems, but oftentimes they work out. So you may not necessarily need to change units to standard units until the end of a problem. If you want to do that ahead of time, you can, but oftentimes you're multiplying and dividing by the same non-standard units, and so you may end up getting an answer that's just fine. 45, 59, 63, the last three. I like 45, pretty cool. Someone shooting a package to send to somebody to get rescued. It'd be kind of hilarious if it landed on top of them, but oh well, a little bit risky there. So the first thing is you want to find the falling time. If you know the falling time, then you know this distance. You can figure out how fast the object has to be thrown or shoved across the river to actually make it to the other side in a parabolic type pattern. So that's 4.7 meters per second. So you're going to use a rocket to impale this package and send it over there. Pretty hilarious. So the initial momentum of just the rocket should equal the final momentum of the rocket plus the package. I just can foresee so many problems with this. So anyhow, the rocket's only 1 kilogram. The rocket plus the package would be 6 kilograms. So that's going to end up being about 28 meters per second. A little over 28. For 59, I like this because it shows that really momentum is conserved on all scales. It's actually pretty cool. It's conserved subatomically as well. This is used for a lot of modern physics, a lot of modern electronic type of things. So you've got a proton that's 1 mass unit. Again, notice non-standard unit. It's going in at 2.5 million meters per second. It bounces back at 3/4 of the speed. Because it's bouncing backward, we're going to call that a negative velocity. So the change in velocity is going to be really the added addition of those two together. So that's over here, multiplied by the 1 unit of mass. That tells us then that change in momentum of the proton will equal the change in momentum of the nucleus. The nucleus shot out at 3.12 times 10 to the 5th meters per second. So the nucleus has to be 14 times as massive. So again, pretty neat. Um, Number 63 is really another vector problem. That's very similar to the one up here with 38. So for 63, you have 3 blobs of clay. I think there was another problem close to this, maybe 62 or 64, that had 3 cars colliding. So I drew the picture because I think that's important. I labeled this one 1, this 2, and this 3. I set up a T-chart. We often did that in AP Physics 1 to determine things vectorially. So get the momentum of this first. That's 160 gram meters per second, 90 gram meters per second, 40 gram meters per second. And then I get the components of this going to the south and to the east. I labeled this north and east. You could label it south and east if you want. Just be consistent with the numbers. So if this thing is going to the southeast and I called this north, this would be a negative component. So I used trig to get that. Use trig to get this. It's a 45-degree angle, so that was easy. This one's momentum was all going to the west, so that's negative 90 east. This one was all going north, so that's positive 40. So I end up getting negative 73 gram meters per second north, positive 23 gram meters per second east. Draw the triangle. Get that total net momentum. But then to get the speed, I've got to divide the total net momentum by the total mass, because these three are all sticking together now. So that's changed. It's 90 grams. So I get 0.85 meters per second. And I use inverse tangent of this triangle to get the direction. So it's about 18 degrees east of south. So hopefully those went okay. Not super complicated, but conservation of momentum is a very universal concept. It comes into play in lots of places. And oftentimes it's not an entire problem on an AP Physics free response, but it would be part of one.